all human beings are different from each other, or we can say that each one of us is unique. Similarly, all the chemical elements are unique, which can be proved by their line spectrum. Have you ever wondered how the chemical composition of distant stars, galaxies, and other celestial objects is predicted? This prediction is based on spectroscopy, the fabulous method of analysis of light radiated by these objects. Every element, when excited either on account of heating or by passing an electric discharge, produces a distinct spectrum. Being distinct, it lends the element a unique identity and helps in establishing its presence in any given object, including stars. Can you imagine what the spectrum of the lightest element, hydrogen, looks like? Let's uncover it in this video. The atomic spectrum of hydrogen was first explained by the scientist Niels Bohr, based on the postulates of his atomic model. When an electric discharge of high voltage passes through the discharge tube filled with gaseous hydrogen at low pressure, it lights up with a bright pink glow. If this light is made to pass through a prism, it splits into a pattern of various colors called hydrogen emission spectrum. The spectrum shows 4 distinct lines: red of wavelength 656 nanometers, bluish green of 486 nanometers, blue of 434 nanometers, and violet of wavelength 410 nanometers in its visible region. Besides these 4 distinct lines, there is a series of lines lying in the invisible part of the spectrum, the ultraviolet region, called the Lyman series, and those lying in the infrared region called the Paschen-Brackett-Fund series, all named after the scientists who discovered them. With just one electron in its only orbit, where did all these lines appear from? Let's find out. Take a close look at a sample of hydrogen gas present in a discharge tube. As you can see, there are hundreds of hydrogen molecules moving randomly in the tube. Let's pass an electric discharge through the tube. These molecules split instantly into their individual atoms. A closer look at some of these hydrogen atoms shows that the electrons have got excited to different energy levels. Remember here that according to Bohr, these orbits are associated with a definite amount of energy, and the electron remains confined to these definite paths and nowhere in between. We will study the Bohr's postulates in a separate topic. As told earlier, not all of the numerous hydrogen atoms are excited to the same extent. In some, the electron lifts to the second energy level, while in others it may rise up to the third, fourth, fifth, or even higher energy levels. But then, with higher energy states being unstable, they fall back to lower energy levels. However, this reverse course may also exhibit variations in the degree of their de-excitement in different atoms, and which may not happen in a single jump. It may take multiple jumps for an electron to radiate a photon of a definite wavelength. This wavelength corresponds to the energy difference between the orbit to which the electron is excited and the orbit to which it falls back. For example, if an electron falls back from the third energy level to the second, it emits energy equal to the difference between the energy of these two levels. This equals to 3.03 times 10 raised to the power minus 19 joules. The frequency of this emitted light is 4.57 times 10 raised to the power 14 Hertz. From the frequency, we can calculate the wavelength, which is equal to 656 nanometers. This wavelength lies in the visible region of the spectrum. The human eye perceives this wavelength as red light, and therefore you can observe a red line in the visible region of the spectrum. In the same manner, Any other transition from a level higher than n is equal to 2 gives rise to green, blue, and violet lines in the spectrum. This series of lines in the visible region is called the Balmer series. If an electron falls back from energy level 2 to 1, it emits radiation of a wavelength approximately 122 nanometers. This lies in the UV region of the spectrum, and thus this is not visible to the human eye. This series is called the Lyman series. Thus, any transition of an electron into n equal to 1 gives a line in the UV radiation. Let's see what will happen to all the transitions from n higher than 3 into n equal to 3. We know that the difference in energy levels beyond the third orbit is very small. Hence, all such transitions result in radiations that fall in the IR region, and the series of these lines is called the Paschen series. In a nutshell, electrons of hydrogen undergo various quantized jumps, each corresponding to a definite wavelength between different energy levels, resulting in a large number of discrete lines in the spectrum. To summarize, we have studied that each quantized electron jump from a higher energy level to a lower energy level results in a release of a photon of a specific wavelength, generating a discrete spectral line, and all these lines together constitute the hydrogen spectrum. The series of lines in the hydrogen spectrum are named after their discoverers as Lyman, which involves electronic transition from higher energy levels to n is equal to 1, Balmer to n is equal to 2, Paschen to n is equal to 3, Brackett to n is equal to 4, and Pfund, where transitions are into n is equal to 5 respectively. Rutherford's atomic model was not able to explain the line spectrum of the hydrogen atoms, but another model was able to achieve this. Stay tuned to find out more about these.